Topic of this talk is using Elasticsearch for distributed tracing implementation at Salesforce. I'm Nikhil Jain. I'm Director of Software Engineering at Salesforce in Big Data and Availability Organization. Our sub-team is monitoring cloud, which helps in ensuring Salesforce is highly available by building various tools in the observability space. Sudeep Kumar is a principal engineer in my team who leads our distributed tracing effort and will be speaking shortly. Rajeshwari is also a key contributor in many of the stuff we are presenting today. Let me briefly introduce distributed tracing. It is one of the key pillars of observability. It is a method of tracking application requests as they flow across multiple services. Let us take this example where customer requested to get sales report. This request goes through multiple hops like gateway, edge service, and finally goes through sales service which might be hitting a cache and potentially database. Prediction service goes through database and makes an external call. Tracing highlights any of these requests that exhibit high latency or errors. A single trace is made of a series of tag time intervals known as spans. A span represents a logical unit of work within the request flow. Review this diagram below, which depicts spans generated in the request flow we just saw. Tracer is used in a number of use cases mentioned in this slide. I wanted to highlight a couple of key ones. Computing and publishing the metrics to our metrics analytic platform using tracer data is one of the key usage. We have thousands of real-time computes, which adds a lot of value to our customers. Another one is Tracer generates a real-time service dependency graph of the complicated ecosystem of services and components we have within Salesforce. Let's look at some numbers. We are currently processing 100 plus billion spans every day while maintaining 99.9% availability SLA. We have thousands of computes across hundreds of unique services. Tracer is used by hundreds of automated synthetic tests in the whole ecosystem. I'll hand over to Sudeep now to take us through the rest of the talk.
Hello everyone, my name is Sudeep. I work alongside Nikhil in the distributed tracing team. A little bit of background about myself. I joined Salesforce a year back, and my background is primarily in building large scale distributed platforms, handling huge volumes of structured and unstructured data, targeting specifically use cases within the telemetry and monitoring realm. Yeah, so coming on to this particular slide and this particular diagram, this is actually our backend tracer ingestion pipeline architecture, wherein we start consuming our traces from a Kafka source. Now, the way the traces gets captured on the Kafka source is via user applications and infrastructure applications like Service Mesh, emitting traces onto an endpoint, which is region local, and that particular endpoint service writes onto a Kafka destination. Now, over the wire, we always use the Zipkin format currently. Although our applications can optionally write data or emit data using the OTLP or OpenTelemetry zone format, and we collect them through an agent and export them back to the endpoint on Zipkin format on the wire. Now, as the data is collected onto the Kafka source, we have different S3 consumers. They run in restricted domain, and these S3 consumers write this data onto an S3 location, a centralized location, in Avro file format, and each file is having typically a fixed file size. So they are rotated every 10 MB or so. Now, once the file is closed, the consumers also emit a record, and they get written into an SQS instance. Now, this record contains details like what is the file location which got written into, what is the file size, and some of the other metadata attributes. We have span consumers which actually listen to these messages or the SQS messages, and as they arrive, they now start downloading the files from the S3 location. The trace themselves goes through different kinds of processors wherein they are transformed in many ways. They can be optionally dropped as well based on different filtering criteria, and sometimes enriched and written onto backend Elasticsearch. A group of span consumers always write to one single Elasticsearch, and this is a design simplicity that we have introduced. um, and all our components today emit health metrics. Those gets collected onto a different metric system on which now we can visualize the data and additionally create any alerts on top of it. So we have n number of such Elasticsearch clusters that we can support in our architecture. Sampling strategy. Now, our platform has always used a head-based sampling approach. Now, if you remember Nikhil's numbers a few slides back, he mentioned that we support around 100 billion spans a minute. Now, this is fairly large amount of data, and which is again sample data. Now we want to move towards more intelligent tailway sampling, which is definitely planned in our future product iterations. But apart from this head-based sampling, we also have an adaptive sampling implemented on our backend. Now this is done really to protect our Elasticsearch clusters from large volumes of sporadic traffic that can come in and really create issues on our Elasticsearch clusters or create latency or lag for our consumption in general. So for to do this, what we have done is we've done an extensive benchmarking on our infrastructure, including Elasticsearch, to come up with a number that we know we can support on our platform, a threshold. And anytime we see a span volume which exceeds this threshold, we automatically adaptive sample and then bring down the overall traffic to more manageable levels within the thresholds that we can support. Now, this has really served us well and has helped us give good availability on our ingestion pipeline. Apart from this, we have now the ability to block spans on some common tag attributes like data centers or region. So once a trace is persisted, now you can visualize this data using a construct called as trace transaction, which is nothing but a hierarchical representation of a trace with a parent and a child relationship. You can say that I want to see a particular trace context with a particular parent and a child and a specific tag attributes as well. Now once you create this transaction, you can share it to other users. They can clone it and again reshare them. But upon executing the transaction, what you get is a time series representation of the trace data, which looks something like this. On the left side, you would actually get all your transaction names, which is nothing but your span name or the operation name. Upon highlighting a transaction name, you get a corresponding trace ID view. You can drill down on a trace and you get a waterfall model like this with if you look at this particular trace, it went through three different services represented by three different color legends here. But actually this information is stitched on the query time directly from Elasticsearch clusters. And we also use Elasticsearch clusters to run a bunch of aggregation queries through which we give things like sum, count, average, and so forth. You can also create metrics on top of this transaction data by now saying that, okay, I have this transaction, I want to emit a periodic metric based on additional filter criteria, and we do that. And the way it is done is that we have a scheduler that pulls Elasticsearch cluster and finds out the corresponding metric value and then writes onto our metric platform. Once it is available on our metric platform, you can visualize using our time series visualization tools and also create alerts on top of it. Now apart from this, we also give service dependency, by which you can now say how your service takes dependency on other services, and potentially how other services takes dependency on you. It is represented as a directed graph. If you really look at here, we have three different services, and the edge actually represents the average duration taken from one service to another service. So this is an important topic, and I need to provide a little bit of background here. So when the platform was initially created, we did not really think about how we can create multiple Elasticsearch clusters. So we had this one giant monolithic Elasticsearch cluster to which we kept adding capacity as the traffic increased. But this was not an sustainable model for us, especially it created issues during patching, upgrades, and even it was like a single point of failure. If something happens to the cluster itself, the entire platform was down. So we had to move to a more scalable model, and we use Elasticsearch Federation for it, by which we now started writing different sets of data to different Elasticsearch clusters. So if you remember, we had an S3 location where we have all our trace data collected, and the consumers, based on different SQS notifications, starts downloading those messages, transforms them, enriches them, and writes onto Elasticsearch cluster. But for writing that, we actually use a federated config map. Now our entire all components are actually on Kubernetes, and we use Kubernetes resources for almost any kind of discovery mechanism. So config map is a popular mechanism that we use for discovery of common resources. So the config map here has information about what data goes to what particular Elasticsearch cluster, and even our query ingestion query component, or the query API, knows this information through this same federated config map. Now this has been very scalable for us, and we've been able to actually now have provisioned multiple Elasticsearch cluster using Elasticsearch Federation. You should look at adopting the same if you're not already done. An additional advantage of using federation is that when a query request comes to your query tracer query API, or a query component, you, if you have information about where exactly that data is, you can go and directly fetch the data instead of federating the query and collecting them and then again returning back to the user. Now again, a little bit of insights into our infrastructure and deployment. We are on Kubernetes. We use Spinnaker for our deployment. We use custom helm charts. Currently we don't use Elasticsearch operator because of some security considerations. We are using SSD volumes for our persistence, and our configuration is typically our retention is configurable based on the cluster. We have three master nodes, three coordinating nodes per cluster. We our all our writes are done via the data node, and all our reads are done via the coordinating nodes. Our deployments are always easy aware with three replicas. We use the open source curator for all our index management, like index purging, index settings, and so forth. We briefly talked about this topic of data sharding, wherein we said that each consumer group actually listens to a particular data set only, and they write all the data into one single Elasticsearch clusters. And the way we have actually separated this data set is by understanding our users' query patterns. Now, the users typically would want to start from a particular data center or region, or any kind of different other constructs. So, it is important to understand that and take advantage of this, especially when it comes to understanding your deployment patterns. Now, having data localization that way, you can now support like partial failures. You will also have increased search throughput, wherein now your if you know exactly where your data is, you on your query layer, you can target your all your searches to that particular cluster only, instead of federating it across all your Elasticsearch clusters and collecting them and returning back the results to the users, which is also more error prone. Now, we also monitor our Elasticsearch clusters extensively, and this is done by our own Python scripts that we have written by querying the node or stats API. We are moving to an agent model more recently, but essentially all this our health data gets collected onto a centralized metric system, on top of which now you can actually visualize all the health of your Elasticsearch clusters. Now these are canned dashboards. For example, here you can see one of our metric which is depicting the disk usage on our cluster. Optimizing writes on Elasticsearch. Now, there are multiple aspects to it, but an important aspect to consider is to configure your bulk API payload size correctly. So, we try different configurations, and the one that worked for us is 1 MB, but it can really vary. Elasticsearch comes up to using 5 MB. So, I would urge you to do your own benchmarking on the infrastructure and find out what's the right value for you. But other than that, right, typically your systems or infrastructure are multi-tenant in nature. So you will have multiple pods sharing the same underlying host, and they are competing for your disk IO bandwidth and your network via bandwidth. So you need to be aware of that. For example, if you consider the left side, which is like a before, and the right is after. So when we initially started off, we had multiple shards of the same index placed on the same um, pod, and due to which we were seeing decreased write throughput. So instead of that, what we decided to use is to flip that model into something on the right, wherein each shard of an index goes on its own pod. There may be a lot more shards initially, but you are effectively using 80% of our cluster for on the write cycle. So, and your indexes are typically created every day or in every hour. So you write all that indexes, and afterwards you have also the ability to shrink those shards into much lower numbers. So we try to take advantage of that, and we have been able to increase our write throughput by moving to a model on the right, where we have only one shard per index per pod on an every active write cycle. Some other considerations that you may want to keep in mind is that not every tag attributes needs to be indexed. So the tag attributes are really free constructs, anybody can create them as they want. So you don't want to really index all of that, because what would eventually happen is that your inverted index will get really bloated up, and it will also take an effect on your ingestion throughput. So we don't index everything. We can always index standard tag attributes like your data center region, if they are like very strict, based on some kind of strict schema. We also index some other important attributes on the trace data, like trace id, service name, operation names, and timestamp. One thing that we have taken advantage of, due to the nature of how the tracing platform looks like, we don't really need the data immediately once it is written. So we have set a refresh rate of 30 seconds. Typically by default in Elasticsearch it is 1 second, by which we've been able to now get more write throughput on Elasticsearch clusters. Also, if you are on Kubernetes, you may want to consider setting the index assign node timeout delay timeout value to a much higher interval, because pods can always restart due to patching or whatever other reasons. So if the pod goes down, you don't want that membership to immediately go away and start the shards getting assigned to other nodes. So have this value set to a higher value. We also use custom Kubernetes readiness and availability probes, and this we have come up with many iterations, and you may want to consider coming up with your own based on your infrastructure and supporting components or systems that you have built. And bulk API, as I said, that always use it for your writes, and always have start with an increased batch size and look at what really works for you. And for us that size has been like 1 MB. Yeah, with this I'd like to conclude our presentation. Thank you. Hopefully there was something that you all learned from this, and have a great day ahead.